Guys, today we're here to talk about multi-step heat problems. Uh, energy changes associated when we're changing temperature and phase. We're going to combine those today. So, quick recap on stuff we did the last two lessons. So, first, we talked about potential energy changes when we're changing phase. So, our kinetic energy in these places is constant. So, we're talking about changes in potential energy. We know our kinetic energy is constant because our temperature is constant when we are melting and boiling, or the reverse process, condensing and freezing as well. So we're going to use that Q equals M delta H. Write down the bolded points. So heat transfer and a phase change. We're going to use Q equals M times delta H, where delta H is the enthalpy of vaporization or fusion or sublimation even, or deposition, one of those enthalpies. So temperature is constant, but we are still transferring energy. Can't use Q equals MC delta T. I know we did that in the last lesson, but our delta T is 0. So that doesn't make any sense here. And we know we'll talk about next and recap why we can't use that for this. We have to use our heat of fusion, heat of vaporization, and we have our constants here. Don't write this down. You already have this in their notes. Our heat of vaporization associated with the liquid to gas is 2,300 joules per gram for water. And heat of fusion, the energy associated with liquid to solid phase change, that's the heat of fusion, is 330 joules per gram. We use MC delta T when we are talking about kinetic energy changes because kinetic energy directly relates to temperature change. So you're talking about changing the temperature of one of the phases. Now, it can be heating up ice, liquid, or gas, or water, or any substance. But they do have different specific heats. So those will be given to you, but you have to make sure that you look for those. So write that down. Heat transfer when you're changing a temperature within a phase, we use Q equals MC delta T, where M is mass, C is specific heat capacity, and delta T is the temperature change within that phase. So let's talk about this. Let's talk about a multi-step problem and a couple of the strategies we're going to use. So how much energy is required to convert 48 grams of water liquid at 25 Celsius to water gas at 125 degrees Celsius? Assume standard pressure. We can't just use MC delta T because we got a phase change here. We got liquid to gas. And we go through that temperature change. Which specific heat do we use? Do we use liquid or gas? In fact, we're going to have to use both. We have to incorporate that phase change and a couple temperature changes here. So let's just dive right into it. Okay? It's going to be a three-part process here. My first part, I have to get my liquid water to its boiling point. At 1 atmosphere, water boils at 100 degrees Celsius. Then I have to boil my water. I have to get it from a liquid to a gas. So I have to account for the potential energy changes here. That's my second part. My third part, I need to heat the gas up from the boiling point to 125 degrees Celsius. Again, I'm changing my kinetic energy. So there's going to be a three-part problem here. All right. So we're going to have to account for all of these three. So really, this question here actually ends up being three parts. And we need to account for each step individually. So write down the bolded points. You can pause here. And you can even try to attempt this problem if you want. So now is a good time to pause. Otherwise, we're going to move on. So the first part, we're going to heat the liquid water from 25 Celsius to the boiling point. Second part, boiling the water. And the third part, heating the gas. So notice I've given you the specific heats here. The specific heat for liquid water is 4.184 joules per gram degrees Celsius. Heating the gas, the specific heat of gaseous water is 2.0 joules per gram degrees Celsius. And the heat of vaporization associated with liquid to gas phase changes for water is 2,300 joules per gram. Now, moving on, let's talk about this. Let's do all this. Okay. So I have 48 grams. So the mass is going to be the same for all of them. All right. So why don't you guys take a minute and if you haven't calculated it, try it. Otherwise, I'll move on. All right. So let's do this. How much energy does it take to heat 48 grams of liquid water at 25 Celsius to water gas at 125 Celsius? First thing I have to do is figure out how much heat it's going to take to change the temperature to the boiling point. I'm using my MC delta T because I got my temperature change here. Next part, I got my M delta H. I'm talking about the phase change. And here I got my MC delta T, again, a temperature change. Whenever I see that temperature change, that's when I'm going to use my MC delta T. Okay, so let's do this. Try to calculate each part now if you haven't yet. And I'm going to go over it right now. So first part, mass, 48 grams times 4.184 joules per gram degrees Celsius times 75 degrees Celsius. And I get, for second part, 48 grams times 2,300 joules per gram. That's the heat of vaporization. Third part, 48 grams times 2.0 joules per gram degrees Celsius times that 25 degrees Celsius. Again, using that MC delta T when I have a temperature change. So I can do these three calculations individually. First one is 15,100 joules. Second one is 110,400 joules. And the third one is 7,200 joules. So see how much more energy it takes to boil than it does to change the temperature. It takes a lot more energy. It takes a ton of energy to do that. So all I do is add up these three values, and then I can get my total energy it takes to get from 48 grams of water at 25 degrees Celsius to water gas at 125 degrees Celsius. All right, guys. So that's it. We're going to do some examples of these problems when we in class on tomorrow.